Hey everybody, and welcome to a video on base rate neglect, or the base rate fallacy. To help us understand this fallacy, it's helpful to start with an example. So we'll start with the sort of example that's common in these discussions. It'll be a medical diagnosis example. So suppose we have a pretty reliable test that's used to diagnose disease X, and it's reliable in the sense that 99% of people with the disease will get a positive test result if they take the test. The test tends to capture those people who actually have the disease. Well, only 1% of healthy people would get a positive result, right? So a reliable test. We can think of this in terms of the inductive strength of arguments by saying that the following is an inductively strong argument, right? Person A has disease X, therefore person A tests positive. That's a strong argument given the specified reliability of the test. Whereas the following is an inductively weak argument. Person A does not have disease X, therefore person A tests positive. Right? Person A having the disease supports the claim that they're going to test positive. Person A not having the disease does not support the claim that they're going to test positive. Now suppose that the general prevalence of disease X in the population, that is its base rate, is 1 in a million. So if we just randomly selected one person from the population, there'd be a 1 in a million chance that they were afflicted with disease X. Now our question is, how likely is it that a random person who gets a positive test result actually has disease X? That is, we want to estimate the inductive probability of this argument. Premise, person A has tested positive for disease X, therefore person A has disease X. Right? This is the sort of inference that we're often interested in the case of medical diagnosis, right? We observe a test result, a positive test. We want to infer to the person having the disease, right? So we want to know what's the inductive probability of this argument, and we can allow ourselves to suppress premises, statements identifying the base rate and the reliability of the test. So we assume that as part of our stock of background knowledge. We're going to see in a couple weeks that Bayes' theorem will give us a rigorous way of figuring out what this inductive probability is. But if we just intuitively estimate what the probability is, we're inclined to tend to get it wrong, right? Most people are surprised to learn how low the inductive probability of this argument is, right? Given how reliable the test is, we tend to think, oh, this is probably a fairly inductively strong argument. The reason we tend to get this wrong is due to the fact that humans commonly ignore the information contained in the base rate when estimating inductive probabilities, right? And doing so we call base rate neglect or the base rate fallacy. And the antidote to this really is to rigorously apply Bayes' theorem, which we'll show how to do in a couple weeks. It's helpful though, at least for me intuitively, to see this through a picture, right? So how is it possible for a test to be really reliable and yet for it to be the case that even when someone gets a positive test result, it can still be unlikely for them to actually have the disease? Well, suppose this is our population of people here, right, represented by all these different faces. And suppose that the 5 faces on the right that look sort of sad and crying, those are our sick individuals. Those are the individuals that have disease X. All right, so it's a fairly small percentage of the population. It's a fairly low base rate. Now suppose we have a test that tests for disease X, and it's reliable in the sense that it's going to tend to capture the people who have the disease. So if we were to test the 5 people who had the disease X, in most cases we would get a positive test result. So this red box represents getting a positive test result. So 4 out of 5 times we're going to get a positive test result when administering the test to people who have the disease, right? We only get a false negative in 1 out of 5. If we test people who are healthy, we tend to get negatives, right? So the blue box is the negatives, red box is the positives. So we tend to get a negative result the vast majority of the time, which is what we want from a reliable test, right? So if you don't have the disease, you're probably going to get a negative test result. If you do have the disease, you're probably going to get a positive test result. But if we put everything together, right, and suppose we administered the test to everybody in the population, we would see that among those who get a positive test result, the majority actually fail to have the disease, right? We have let's see, 6 people who get a positive test result and they're healthy, and only 4 people who get a positive test result and they're sick. So just if you're just a random person, you get a positive test result, there's still a better than 50% chance that you don't have the disease, right? So the test is not entirely diagnostic. The reason is that the base rate of the disease is sufficiently low in the population, even though the test is relatively reliable. Now, of course, if we up to the reliability test further, or if we up to the base rate of the disease, then the test would become much more diagnostic. All right, so hopefully this sort of story in pictures helps you see what's going on in the case of the base rate fallacy. So what should our takeaway be here? Well, our takeaway can be to not ignore base rates when we're estimating the inductive probability of arguments. And also, we don't want to confuse the support that P provides for Q with the support that Q provides for P. So if we go back, right, we were interested in how much support does a positive test result provide the claim that the test subject actually has a disease. That was the probability we were interested in. And we knew the reverse of that, right? We knew how much having the disease supported testing positive, right? But those are different numbers, right? And it could be the case that having the disease strongly supports getting a positive test result, but getting a positive test result doesn't strongly support having the disease, right? So the trick for us is going to be to use Bayes' theorem, right? Because this is another case of us having humans tending to have a systematic error in our judgment or estimation of inductive probabilities. So in the scientific inductive logic that we'll develop in a couple of weeks, Bayes' theorem will be a centerpiece of that, and we can use it to compute posterior probabilities of things like the probability that you'd have the disease given you got a positive test result. So we can look forward to that. Please complete the participation poll for this video, and thanks for watching.